Good morning, class. So today we are continuing in Chapter 4 and we are beginning in Chapter Section 4.2. So, what's the big deal for today's lecture? Well, really, we're going to be doing a bunch of sketching. We're going to take together all of what we've learned so far. What are derivatives? How do we take derivatives? What's the first derivative? What's the second derivative? What are critical points? What are hypercritical points? Finding local min and max. Um, Finding points of inflection, so on and so forth. We're going to use all of this stuff we've got so far, put it together, and we're going to use it to be able to sketch what graphs look like. Now, this is especially useful for maybe you have a function and you don't have a graphing calculator or you don't have access to Desmos or something, but you want to know how a function looks. Well, using the techniques we learned today, we're going to talk about how you can draw an accurate picture for any polynomial function, whatever the function is. Um, the other thing this will be useful for is maybe you're given information about, okay, I have a function that's increasing here, it's decreasing over here, I know it's concave down here, I know it's concave up over here, but I don't know what the function actually is. I don't have the actual equation for the function. Well, that's okay because based on what we have so far, we're going to be able to draw a picture of the function without even knowing what the function is. So that's really where the power of this kind of stuff comes into play here. So let's go ahead and get started. So we are aiming to learn how to sketch polynomial functions specifically. So this is section 4.2, and just as a little refresher, what is a polynomial function? Well, a polynomial function, call it p of x, is really if it's any coefficient a times x to some power, we could call it, I don't know, we could call it c. And then maybe we got a plus, and there's a b, there's another power, and then x raised to, I don't know, d. And this can go on and on and on until you get to x by itself to some other power, or times some other coefficient, plus some final constant f. Whatever. This is a polynomial function when you have an equation in this format, where it's just a linear combination where we're adding and subtracting x's to different powers with different coefficients on them. So after today, you're going to be able to look at any polynomial function and know how to graph it. So let's go ahead and get started. So for the sake of simplicity, of course we're going to have some examples we'll talk about, and I'll take you through each step one by one so you'll see what we're doing. But beyond that, in terms of the notes for this section, I'm just going to give you a step-by-step guideline for what you need to do. And if you follow these steps in the correct order, well, really, even if you flip the order a little bit, I think you should still turn out with the correct answer. But I'm going to give you what I think is the best order, what I think makes sense, and then we're going to talk about it. So, sketching polynomial functions. So, step one, what do we do? Well, you need to find f prime of x and f double prime of x. Why? Well, in order to use f prime of x and f double prime of x, we use these things to find what are our critical points, what are our hypercritical points. And you have to have these two before you can label them. So the first step is just to find what those equations are. Now sometimes the question will give you what these are, and they won't tell you what f of x is. So sometimes this first step is already completed for you, but regardless, the first thing you have to recognize is that you're going to need these two guys one way or another. So what do we have so far when we're trying to graph something? We need f prime, the first derivative, and then I'm going to draw right below it the number line for f double prime, the second derivative. Why? Well, as I move forward in these steps, you're going to see that as I put more stuff on these lines and I start to label this stuff, it's going to be very useful when we try to when we try to draw a hypothetical graph. And this is purely for demonstration. This is not an actual function or an actual problem. This is just that you can see visually what I'm doing for each step. So far all we've done is we have our first derivative and second derivative. That's it. Okay, then what? What do we do? Next, find critical points. And remember that critical points are where the first derivative equals 0. They are also potential local extrema. And recall that a local max or a local min is where the first derivative changes from increasing to decreasing or vice versa. So first step, find your critical points. And I'm just going to label them here on the first derivative with C1 and C2. Maybe for this demonstration we only have these two critical points. So I've labeled them and I'm trying to line them up with where they are on my graph here. Because when we start working through examples, it's going to be very useful to draw these number lines below your graph and then label the same x points for where our critical points and where our hypercritical points will be. So this is very useful here. All right, so what's next? So for step 3, we now want to label intervals of increasing, decreasing. And I'm running out of room over here on the right side, but you get the idea. Label intervals of increasing and decreasing. Now again, sometimes the problem will just flat out tell you that, hey, it's increasing for this interval and this interval. But the point is that you have to take that information that they'll tell you in words and you need to translate it into what it means graphically. What does it mean on this number line? So let's see. Maybe we're increasing in the middle and maybe we're decreasing after C2, and then maybe we're increasing to the left of C1. So we now have these labeled intervals for increasing and decreasing. So then what's next? Step 4. So based on these labels, find local extrema. And this is based on the first derivative test. So from the first derivative test, I can see that at C2, it's increasing and then it's decreasing. So what does that make C2? This is a local max. Now all that means is that I can put some small interval around C2 and it's going to be the biggest value for that little region. It could be that it's not actually the maximum for the entire function, but at the very least, it is the maximum for some region in this area, very locally, because it's increasing and decreasing at that point, so we got some little bump there. Okay, so let's keep going. What's next? We have a local max, and based on this, we don't have any local mins, so we're done with step 4. So what's next? Step 5. Find hypercritical points. So this is where the second derivative is equal to 0 or is undefined. Hypercritical points are also useful for labeling, where do we have these places where the second derivative isn't positive or negative. And then when we check the intervals that are in between these hypercritical points, those are the places where we know the function is going to be concave up or concave down. So this is very useful for telling, okay, well maybe I have a function that's increasing, but is it increasing in a concave up fashion? So this would be increasing and concave up. And then, or is it increasing but concave down? So that would look like this. It's still increasing, but it's concave down. So it's very important to distinguish between the two because graphically these are two very different lines. And so by combining both of the information of increasing and concave down or increasing and concave up, you get different pictures. So this is an important distinction here. So we'll find hypercritical points. And so for the sake of this example, let's say we have 2, and we'll say that they're at the same points. So C1 and C2, maybe they just happen to be hypercritical points also. Okay, well now what? Well, we have our hypercritical points labeled now, and this is where we move on to step 6, and we label intervals of concave up or down. And again, depending on the question, maybe they'll just give you the equation for the second derivative, so you'll be able to set it equal to 0, find your hypercritical points, and then plug in numbers in between to figure it out. Or sometimes the question just might tell you, yeah, for this region, it's increasing, and yeah, over here, it's decreasing. And the question might just tell it to you in regular English, and then it will expect you to take that information and translate it to what it would look like on a graph. So this section is very much all about graphing. Do you understand what these words look like? It's all fine and good to find your critical points and to find your hypercritical points. It's all fine and good to know that it's increasing here, or maybe it's concave down over there, but do you know what that looks like graphically? And that's the whole point of this section here that we're covering. So, label intervals of concave up and concave down. So, okay, maybe we're, let's see, let me think about this a little bit. I don't want to make it too easy. Yeah, let's say we're concave down here. So I'm going to use a down arrow for concave down. It's curving downward. Let's say I'm concave up here in the middle. And then here on the left side, let's say I'm concave down again. Okay, so I've labeled my concavity. So what's next? Find points of inflection. So just as with the first derivative, if you find places where the positive negative flips to either side of a hypercritical point, then again, as we've discussed previously, that's a hypercritical point. It's a place where the concavity changes signs. So hypercritical point. Okay, so far so good. Now what? Now we're finally ready to begin sketching. And then note here that starting points are helpful here. And what do I mean by a starting point? Well, oftentimes with these types of questions, they'll say, given, maybe we know f of C1 is equal to, let's say, 2. And maybe we know that f of C2 is equal to 6. And this is just information they give you. So as a part of this question, maybe they would tell you about what the first derivative and second derivative is doing. And maybe they would give you these 2 points, but maybe they don't tell you what the original equation is. So you still can't just type it into a calculator because you don't have the equation. But based off of these 2 points and all the information I have written here, I'm still going to be able to draw it. How? Well, let's just take a look. So I'm given at C1, I have a value of 2. So here's C1, 2. I just put a point there. And then at C2, I'm told it's 6. So that's, let's see, 3, 4, 5, 6. And with these graphs, it often helps to draw it to scale. It'll make it look better. So that's why I'm trying to be careful about how I count this out. And there we go. Now for this left side, for this area to the left of C1, I'm told it's increasing. So as I approach C1, I'm getting bigger and bigger and bigger. I'm increasing to C1. So the y values to the left are lower than C1 if I'm increasing up to it. But I'm also told it's concave down. So I should have a curve that's facing downward. If I were to pour water over it, then the water should just slide off. It's not going to be able to hold water. It doesn't have a bowl shape. So that means if it's increasing and concave down, then maybe it looks something like this. Now, of course, this is just a sketch. I don't know if it crosses the x-axis here or not, but I know it's going to have to cross the x-axis somewhere since it's concave down and it's also increasing. So, okay, we've got this first part drawn. Okay, great. So let's look at the second part, this area in the middle. We're told that it's increasing. So from C1 to C2, we're increasing, which makes sense. I mean, in order to get up there, we're going to have to increase. We're also told it's concave up. So the curve should be facing upward. And so if I were to pour water over it, it should be able to hold at least some amount of water. So here we go. We're increasing and we are concave up. So something like this. I have the curve facing upward, but it's also gently increasing. And I know it has to look like this because there are only two ways to increase. Well, I guess three ways. You could, one, increase like this. This would be concave down. Or you could increase like this. That would be concave up. And as a third case, I guess you could increase with just a constant line. But in that case, there's no concavity with a flat line like this. It doesn't have concavity facing upwards or downwards, so it's a concavity of 0 for the entire function. So there's three ways to increase. But because it's concave up, I know it has to be this third option here. Okay, so we're almost there. And now for this last step, for this section that's to the right of C2, we know that it is decreasing and it is concave down. So the curve should be facing downward as I decrease. And so it should look something like this. And there you have it. So admittedly, yeah, this is kind of a strange looking thing. But with these kind of questions, you often end up with graphs that kind of look strange like this. But this is it. We're now completely done. And we were able to put all of this together just based off of the first derivative, the second derivative, and these 2 points. That's all we needed to be able to sketch what this graph looks like. And admittedly, we should highlight the fact that this is a sketch. We don't know for an exact fact that it looks like this. Well, I mean, we don't know exactly that it crosses the x-axis here and here, I mean. But we know that in general, the shape of this graph is going to look something like this. So it's an estimate, but it's a very educated guess. And so we call it sketching. All right. So we've walked through the steps, and I've kind of had this semi-quasi demonstration here on the left with what this is going to look like visually. But now let's actually look at what a question will actually say, what a question will actually give you to work with. So I'm going to start by, and I should also note, so in that last one, the questions we had about the sketch were, we don't know where it crosses the x-axis. We also didn't know where it crosses the y-axis. So among these helpful points to help you get started, it's also nice to know x and y intercepts. And if you're lucky, sometimes the question will give it to you, but if it doesn't, that's okay. If it gives you an equation, then you can solve for these guys, and then you'll know exactly where it crosses the x-axis and where it crosses the y-axis. So, useful stuff there. Keep that in mind. All right, so let's take a look at what a question might actually give you. So we're starting out with a simple example. And here, yeah, this is what I was talking about. So they don't give us any equation at all. Instead, here's what they do. They give you a list of points that they consider to be facts for this graph, and then based off of those facts, they want you to sketch it. So what do they say? They say, sketch a continuous function that satisfies all of the following conditions. What conditions? Well, 1, f of -1 is equal to 2. So like in that previous demonstration, I said at the very end that sometimes a point will be given to you. This is a given point. This will be a starting point we can use when we're ready to graph it. All right, so they give us this point. What else? 2, f prime of -1 is equal to 0. So this is a critical point. We want to make sure we label that on our number line we'll draw for the first derivative. So this is good. That's a critical point. 3, we're told that f prime of x is less than 0, so it's negative, which means it's decreasing. So that means decreasing for x less than -1. Okay, so that's giving us an interval. For all x is less than this critical point, we're going to have negatives. All right, what else do they give us? 4, f prime of x is greater than 0, so that's a positive, so it's increasing for x greater than -1. So for x's that are to the left of our -1, to the right of our critical point, it's going to be increasing. Okay, so what else? They've already given us a lot of information here. 5, they tell us the second derivative is greater than 0, so that means concave up for all x. So that means for our entire function here, it's concave up. The curve is facing upwards. Okay, so that's nice. That's going to help us when we try to draw this. And now what? Well, that's all the information they give us. But based off this information and the steps we have here to the right, we're good to go. So what do? Well, step 1, find f prime and f double prime. Well, we don't know what those equations are, but we are given through 2 and 5, we're given all we need to know about the intervals for these areas. Okay, so that's pretty good. We already have these. Find critical points. Okay, well, we have a critical point. So this is for f prime of x, the first derivative. We have a critical point at -1. So I'm going to put -1 here. There's my critical point. Okay, check. We've done that. Step 3, label intervals of increasing or decreasing. Now, luckily, as you can see in number 3 and 4 over here, they give us that. So the derivative is less than 0, so it's decreasing for x to the left of -1. So we are decreasing over here. And then to the right of -1, in 4, we're told it's increasing. Okay, good so far. Now what? Well, now in 4, it wants us to find local extrema. So what's a local extrema? Well, based on the first derivative test, it's where the first derivative changes signs. So here, it's decreasing and then increasing. This is a local min. Okay, good so far. Now what? Step 5, find hypercritical points. Well, hypercritical points are where the second derivative are equal to 0. However, in this case, in step 5, or not step 5, in number 5 here, we're told that the second derivative is positive, for all x. In other words, there is no x anywhere where this second derivative could equal 0 because it's positive everywhere. And if it's positive everywhere, then we have no hypercritical points. Okay, so nothing to label there. Let's keep going. 6. Label intervals of concave up and concave down. So now we draw our number line for the second derivative. And we want to label concavity. Well, we're already told that it's positive everywhere, which means it's concave up everywhere. So the curve is facing upwards everywhere. So this is positive everywhere. Okay, now what? Points of inflection. Well, points of inflection occur at hypercritical points. We don't have any hypercritical points, and so we don't have any points of inflection. So we can skip that step. Going on to step 8, we're ready to start sketching. Starting points are helpful. Okay, so here let me use a different marker for contrast. So here's our line. Here's x. Here's f of x for the y-axis. Let's see, we've got a point at -1. So at -1, it's equal to 2. So 1, 2. We have a point right there. Okay, now what? Well, now, just as we did previously, I'm going to use the information from these lines down here to draw everything to the left and to the right of it. So to the right, I'm told it's increasing, so it's going upwards, and it's concave up, so I should be going up with a curve facing upward. So what does that look like? Well, that looks something like that. Concave up. Okay, now for the left side, I'm told that it's decreasing as it approaches -1. So as we approach x equals -1, our slope is negative. It's a decreasing function, which means we're coming from above. So if we're decreasing towards this point, then we're coming downwards, but we're also told it's concave up. So as we come down, we should be curving such that the curve faces upwards as we decrease. So the graph on this side is going to look something like that. And when we draw it like this, we have our local min here, so it's labeled. It makes sense. It is a minimum for this graph. And in fact, based off of this information and based off of these labels here, it actually looks like this is probably an absolute minimum. So we have a local min at x equals -1, but we also have a absolute min at x equals -1. And we know that it's absolute because everything to the right of it is bigger. It's increasing, so nothing to the right will ever be smaller than it. And to the left, we had to decrease to get towards it. That's for all of the x's to the left of it. So if you have to decrease to get to it, then there's no x values over here that are going to result in an f of x that are smaller than it. So it must be an absolute minimum. So there we go. This problem is now done. We have our graph. We have local min. We have an absolute min. There's no maximum here because it increases infinitely on both sides. But that's fine. No big deal. And now we're done. And in order to do this problem, we had to combine all of our knowledge from the first derivative test, the second derivative test, and our definitions for extrema, critical points, hypercritical points, local mins and maxes, and absolute mins and maxes. So this lecture really culminates in bringing everything together, and now we get to see it visually. So this is really nice as a tipping point for chapter 4. All right, so what's next? What else can they throw at us? Because that was an easier example. That was concave up everywhere, which makes it easier to draw. Yeah, okay, so there's 2 examples here I want to talk about. Well, 3 examples. So the first thing, and just to switch gears so we're not graphing for a second, so you don't have to stress out about trying to sketch something. Let's switch to a different kind of question you might get during section 4.2. All right. So a possible question you might get would be, suppose that g of x, so g of x is equal to 5 halves x cubed plus s, so s is some variable we don't know yet, s x squared minus 6x plus 1. So suppose that g of x has an inflection point at x equals 3. Well, recall, what is an inflection point? An inflection point is where concavity changes signs to the left and right of the point. But in order to change signs, that means it had to have been 0 or undefined at that point, which means x equals 3 is a hypercritical point. Okay, so good to know. So now what? So now the question says determine the value of s. So based off of this information, we can actually figure out what s has to be. So this is more of like an algebraic type question that you might get during section 4.2. So how do we solve this? Well, in order to be a hypercritical point, that's where the second derivative is equal to 0. So if we find our second derivative and set it equal to 0, and we plug in the fact that this happens when x equals 3, that's going to get us well on our way to finding s. So let's give it a go. So g prime of x is equal to, so we're just going to use our power rule. 3 comes down, so 3 times 5. That's 15 divided by 2, x squared plus 2 times s, x to the first power, minus 6. Now when we're taking derivatives here, and we have these other constants that are labeled as s, or maybe it's b, or a, or d, what have you, for the purposes of taking derivatives, you just treat it as if s is some constant number, which in reality, it is in order to have this hypercritical point here, but we're just trying to figure out what s has to be. So when you're taking your derivative, just treat it as a constant. It's just some regular number. We just don't know what it is. So we have 2 times s, the same as we would for the power rule. And we just leave it at that with the x on the end. Okay, so there's our first derivative. Now we got to take the derivative one more time. So g double prime of x, we get 2 times this fraction, so the 2's will cancel. We'll have 15 times x to the first power. And then here, the derivative of 2sx, well, the x is going to disappear, and we're going to be left with plus 2s. And the derivative of negative 6 is 0. So now what? Well, now we know that the hypercritical point occurs when x equals 3. So let's just plug in x equals 3. So g double prime of 3 is equal to 15 times 3 plus 2s. And the only way this can be a hypercritical point is if this equals 0. So how do we do this? Well, now what we got to do is just solve for s. This is just regular old algebra. So we're going to have 2s on the left. Oops, let me move this equal sign. We're going to have 2s on the left. That's going to be equal to 15 times 3 is 45. So I'm going to subtract it over. We got negative 45 on the right side. Divided by 2, s is equal to negative 45 halves. And that's it. There's our final answer. We're done. We've solved the question. And that's a perfectly valid answer there, and it's okay to leave answers in fractions like that. And there you go. So this question actually isn't so bad to work through, and it's fairly easy once you understand what it's asking you to do. But the point here is to remember your definitions for what is a hypercritical point, or more specifically, because the question only says, it calls it an inflection point. But an inflection point is a hypercritical point, and so you use that information and plug it in with your second derivative to find your s. And there you have it. Let's see. All right, so there was another example kind of like this I wanted to do. So let's go ahead and do it real quick, and then we'll do one more graph problem so you can really sink your teeth into that, and then you should be good to go for this section. Alright, so what's this question asking for? So now we have, suppose f of x is equal to sx squared plus 6x minus 3. So again, we have some unknown s label here. But just as before, we're going to treat it as a constant. Okay, now what? And we're told that we have a maximum at x equals 1. Okay. And then it wants you to find s. Well, recall that a maximum, so in this case, the question doesn't say if it's a local max or if it's just an absolute max. Whatever the case may be, with this question, we're not on an interval. We're not bounded on some AB, which means that this maximum is not like just some point that's on the side of a bound. It has to be some maximum that's true for either the entire function, or maybe it's just true for some small area of the function where it curves up and down. So what does that tell us? Well, that tells us in order to be a maximum on this function, whether it be an absolute or local, we don't know which one it is, it has to be a critical point. So we have a critical point right here. And now that we know that, we can find our first derivative and set it equal to 0. So our first derivative is going to be 2sx plus 6. And we know that when x equals 1, the first derivative is equal to 0. So 2s times 1 is just 2s, plus 6 is equal to 0. So we get 2s is equal to negative 6, and so s equals negative 3. And that's it. Again, we're done. It's a simple enough calculation. The trickiness with this question is really, do you know what it means to be a maximum? And then do you realize that it's a critical point? And then you use that information to figure out what s has to be. And there you have it. So those are two questions you might see during the certified quizzes for today's section. So that covers what I wanted to have there. And then lastly, I wanted to do one more graph problem. So let's give it a go. Where did my book go? Yeah, here we go. So just as before, this just gives us a list of information without telling us what the equation is, and then we're expected to figure out the rest from there. So what do we have? We're told A, f of 0 is equal to 5. F of 4 is equal to also 5. And we're told f of 2 is equal to 1. So they give us a lot of information here with these points. We have a y-intercept here. This is when it crosses the y-axis. So that's nice. And then we got these two other points that'll probably be useful later. B, they tell us f prime at 0 equals 0, and f prime at 3 equals 0. So they've just told us our critical points. Okay, that's useful. What else they got for us? C, they tell us f prime of x is less than 0, so it's decreasing for x less than 3. Okay, so far so good. D, we're told f prime of x is increasing, so it's positive. D, it's increasing for x greater than 3. Okay, that's nice to know. What else do we have? And then they give us e. They say the second derivative is equal to 0 at 0. So now they've given us a hypercritical point. They also tell us the second derivative is equal to 0 at 2. So again, there's another hypercritical point. It's also important to note that when the second derivative is 0, it's neither concave up or concave down. So that's when, at that point, we have kind of a flat line thing going on. So keep that in mind when we try to draw this. And then for f, we're told the second derivative is less than 0 if 0 is less than x is less than 2. So in between 0 and 2, we are concave down. So I'll put a down arrow here. And then lastly, they tell us the second derivative is greater than 0. So that's increasing, that's concave up, if x is less than 0 or x is greater than 2. So outside of this region between 0 and 2, we're told that it's concave up. Okay, this is all useful stuff. Let's see, and what else do they give us? And that's it. Okay, so based off of all this information, we're going to be able to graph our function. So just as before, and I'll switch colors here. Just as before, we want to label our first derivative, and we want to label our second derivative. So what do we have here? We're told we have a critical point at 0. So right in the middle, we got 0. And we've got a critical point at 3. So I'm going to put 3 over here. Let's see. We're told it's negative for x less than 3. That's for all x less than 3. So that means for here and here to the left of 0, it's negative. Now, they kind of made a typo here. They should have specified that this is true for x between 0 and 3 and x less than 0, because we already know at 0 it is 0. So it's not negative for all x less than 3, in particular when x equals 0, but that's just a little slip up on the writer's part. And then we're also told that it's increasing for x greater than 3, so we're positive over here. Okay, now what? We've labeled our first derivative. Now for the second derivative, we have a hypercritical point at 0, and we have a hypercritical point at 2. So that's here in between 0 and 3. And then we're told that in between 0 and 2, the second derivative is negative, so we are concave down here. And then for all other x's, we have that it's concave up. Okay, there we go. So now, as I try to graph this, it's important to label all of these x's because they're points where things are changing, where things are happening. So we've got 0. We've got, and I always try to line it up so that it matches with these two lines I have drawn down here, so it's easier to picture it. And then I've got 3 over here. Yeah, I think that's good enough. What else do we have? Well, we're told at f of 0, going back to the very top of this question, we have at f of 0, it's a value of 5. So 1, 2, 3, 4, 5. And I'll switch markers again. We've got a point at 0, 5. We also have a point at 4. So this is extra information that we didn't have otherwise. We're told at 4, it's also at 5. So there's another point. And then we're told at 2, it's a value of 1. So we got another point right there. Okay, so what do we do with this information? So let's see. We can also label, we can see here that with this negative positive, we have a local min at 3. We can also see from the second derivative that we have points of inflection at both 0 and 2. Why do we care about that? Well, we care about it because it means when we come to those x values on our graph, the concavity should change. So if it's concave up, it should switch to concave down, or vice versa. So as we draw this, we can see that, so for easy starters, we see from the left, it's negative, so we're decreasing as we approach 0. So it's coming from somewhere up above, and it's concave up. So that means that we have something like this. It's decreasing as it approaches 0, and it's also concave up. All right, so far so good. Now what? Well, in between 0 and 2, and it's important to mark this 2 because that's a point of inflection, we have that it's decreasing and it's concave down. So we are decreasing, but the curve is facing downward. So be very careful about this stuff when you're drawing this stuff with the concavity differences. After 2, we see that it changes back to concave up, but between 2 and 3, it's still decreasing. So now we're decreasing still between 2 and 3. So you want to make sure you keep track of this area in between 2 and 3. We're decreasing and it's concave up. So still decreasing, but we're concave up until we hit 3. So what happens at 3, and I don't know if 3 is actually down at this point I have labeled or not. It could be further down, it could be up higher. Point being, this is just a sketch. So I'm decreasing and it's concave up. After 3, it starts to increase again and it stays concave up. So now we're increasing again, we're concave up. And then after 4, it just stays increasing and concave up. Oops. And there we have it. So obviously a very rough sketch, but the point being, that's it for this question, and that would be considered your final answer right there. So things to keep track of, it's very easy to get mixed up where you have these places where your hypercritical points don't match up with your critical points. You want to make sure that you pay attention to these areas between the 2 points, because those are places where it might briefly be one or the other, and then it's going to switch. So watch out for that. That will slip you up, and you want to be careful with that. Otherwise, that's everything I had for today that I wanted to talk about. So I hope that makes sense. Of course, if you have any questions or concerns, don't hesitate to email me. We can talk about it. We also have our Q&A coming up later in the day. So by all means, come to that with any questions you may have. Otherwise, that's all I've got for you, and I wish you the best of luck.